So now we've finally arrived at the last chapter, which is quarks, leptons, and the Big Bang. Basically, in this chapter, we're going to study two really fun and really big questions. Namely, what is the universe made of, and how did the universe come to be the way it is? What the universe is made of is basically this part about quarks and leptons, and how it came to be the way it is now is this part about the Big Bang. Now, in the 1930s, they knew about most of the things that are studied in chemistry and most of physics. They knew that the universe was made up of electrons, protons, and neutrons. And essentially, all of matter that you interact with in your daily life is made up of these three particles. And they're connected via the photon, gamma, which mediates the electric force that holds the electrons around the protons. So in the 1930s, a lot of physicists thought that maybe they had figured out everything about the fundamental nature of matter. They were wrong. Since then, they started discovering new particles, like the muon, which is a heavy brother to the electron, and the pion, which helps explain how the protons and neutrons are stuck together inside of the nucleus. And many other particles started showing up, kaons and many other things. Now, one thing all these particles had in common was that they were unstable. They decay into something else. All of the ones up here are completely stable and exist for long periods of time. The neutron can decay into the proton, and the proton can decay into the neutron, but there are nuclei where they are totally stable with protons and neutrons. These new particles are all unstable. They will eventually decay into some combination of these ones. But they don't appear to be composites of these. Because they decay, they follow a decay rate that says n is equal to n naught e to the negative lambda t, and they have a half-life equal to the log of 2 divided by lambda, or tau, the mean lifetime, times the natural log of 2. These new, more massive, unstable particles actually have a wide range of half-lives or mean lifetimes. They range all the way from 10 to the negative 6, which is one of the longest lived, the muon, seconds, down to things in the neighborhood of 10 to the negative 20 or even 10 to the negative 22 seconds. These are tremendously small half-lives. These things exist for only a bleep of time. In fact, these are such short times that some of these can't even be detected by actually measuring them and seeing them. We often detect them only by things that they decay into. And oftentimes, we can't even measure their mass accurately or the time accurately. Instead, we know the uncertainty relationship, that the uncertainty in energy times the uncertainty in time is less than or equal to h bar over 2. Well, the rest energy is just the mass. And so, sometimes we can measure an object's mass, a particle's mass, but when we measure it and we try to plot its mass, do that, mass divided by number of events. When we plot that, the mass versus the number of events, the mass is often spread out somewhat. It's not really well defined because its lifetime is so small that it never has a well-defined mass. Instead, we call this the peak mass, and we use this width in the measurement of mass to figure out what its very short lifetime is. These new particles also often have very large masses. With such large masses, we need a lot of energy to create them. We do that by taking two particles, either electrons or protons, and smashing them together very fast. To smash them together very fast, we need some kind of an accelerator, very much like the cyclotrons we studied in 102. But much, much bigger. And when you're colliding two things against each other at so many electron volts, such very high energies, currently we're looking for about 7 times 10 to the 12 electron volts in each proton. When you collide things that hard, and they live very short times, you have to have a very sophisticated, very large device to detect them. The current largest devices are probably about 30 meters long and 30 meters wide. This is one of the detectors at the Large Hadron Collider in CERN. I'm not sure if it's ATLAS or CMS, but if you look here, this is the size of a person, and this isn't even the entire detector.